Hello and welcome. This is Group 8's Cybersecurity and Cryptography Press 1 assignment submission. The people working on this group are ST2014-0942, ST2012-4025, and ST2020-9315.
For our introduction, this project we have been tasked to conduct a primary analysis on the efficacy of using secret share scheme when implementing multi-cloud storage. We are doing this on behalf of a firm called Simple Cloud, which is a London-based service provider. Simple Cloud has provided some codes to us, and we are to advise which combination of valuable TNS provide the best service or maybe has the lowest latency. Now let's look at our knowledge. Secret sharing scheme are a secure way of sharing secret information. They work by splitting the information into multiple shares, and a certain threshold must be met in order to recover the original secret message after it being split. For example, where S is equal to 5 and T is equal to 3, the secret will be split into 5 shares, but any 3 of these shares are required to recover the secret. One of the techniques is that the secret can be shared with many individuals, but no one individually can recover the secret on their own. They always need to have other people on board to do so. The storing secret in a distributed way means that a leak from one server or storage node will not allow the attacker to the means or access to reconstruct the secret. Okay, now let's look into the implementation of Ashumi secret sharing for a multi-cloud storage.
Okay, how does storage, retrieval of shares, and recovery of original text works in Python? The first step we're gonna need is write each share in a different file in order to upload each file to the cloud storage bucket. Once we have each file with each share in the cloud storage bucket, we will need to download those files in order to get the content and reconstruct the message. Okay, first of all, we need to open and create these files. Then we will have to write in each file this share, but this share will need to be written in hex, because instead in the Dropbox cloud storage bucket it will get corrupt. So as we can see in the picture, we open the file, we write into the file. First, obviously, we need to take the shares out of the secret, and then we upload the files as we can see in the picture. The time upload is the time that it will take to upload the files. Here we got the download files from the cloud storage bucket. In order to download the files from the cloud storage bucket, we will need to make use of the library Dropbox, and we will calculate the time download using this time download the variable that we can see in the picture. Then we will get the content of the file that has been downloaded by unhexlify, that this will convert the content of the file that is in hex, it will convert it in bytes. That's what we need in order to reconstruct the message. So we will append this content unhexlify to the list rshares, that is the list that we're going to use to reconstruct the message. We do this with each share, and we will be able to reconstruct the message. when talking about the reconstruction of the message, we will have to calculate also the time of reconstruction. We will use the variable time of reconstruction in order to calculate this time. The line of reconstructed underscore secret equal TSS dot reconstruct underscore secret, and we use after all this the list R shares, that is the list that contains the shares that we downloaded previously from the files on the cloud storage bucket. When we make use of this list in order to reconstruct the message, we can reconstruct the message and print it as it's below. For controlling the combinations of S and T in the code, because we need the combinations of T2 and T3 for S3, 4, and 5, we need to control this. So for this, I made a loop of 6 iterations in which S is going to be one value more than in the last iteration. So if S was 3 in the last iteration, in the next one is going to be 4. So that's why T starts with 2 and S starts with 2, because the first one is going to go in the loop and will be not 2, it will be 3, as I just said. So then we have an if clause that will control that only when T is 3 and the counter is 0, that the counter is for the program during the run, only goes once into the if clause. If it goes more than one to this if clause, when T is 3 and S is 3, it would increment one S, and we will lose one combination of T and S. So that's why we need the counter. On the top of the program, we have this that I just explained. And then at the end, we will have this other picture of the if clause. If S equals 5, T is 3, and S is 3, in order to don't lose that last iteration that I just talked about. Here we can see the Dropbox folder with the files with the shares in it. In the first picture, we can see the folder, and this folder, the files that are inside each folder, will be deleted each time the program is run. This is because Dropbox gets corrupted and has errors if you don't delete the files every time you run the program. In the picture below, we can see the content of a share during the running of the program in the Dropbox cloud storage bucket. Here we can see the share that is not in bytes, it's in hex. That's very important, because if not, the file gets corrupt. And we can see the content that it has to be cast to bytes when the download is made.
Okay, so now that the program can split the shares, send them to the cloud, retrieve them, and then reconstruct the secret from the shares, we can start to have a look at some of the results of our investigation. So in this chart, you can see the time to split on the left, which contains the amount of time taken for the program to split the secret into shares, and also to write them to a file and convert them to hex. Then time to upload shows how much time it took for the files to be uploaded to the Dropbox. Time to download shows how much time is taken to retrieve the files from the cloud. And then time to reconstruct shows us how much time was taken by the program when converting these shares back from hex and reconstructing the secret. Latency is also probably the most important variable here on the right, and is the sum of time to upload and time to download. In this chart we can see that the less shares produced while t equals 2 reduce the amount of time taken to upload and download the files. This would make sense as there are less files to be sent. When collecting this data, we ran every combination of variables through the program 10 times in order to collect an average amount of time taken. These values were then put into the table you see now. On this page we can see that the latency follows the same trend as established in the previous slides, where the lower the value of s, the lower the latency. Okay, so we can now compare the results from the last two tables. So let's have a look at, for example, where s is equal to 4 and t is equal to 2, and also where s is equal to 4 and t is equal to 3, where the only thing that has changed is the number of shares required to reconstruct the secret. We can see that the latency from where t is equal to 2 is lower than the latency where t is equal to 3 by about 0.6. Additionally, we can also see that the time to reconstruct has been increased where t is larger. By here we can see that despite the fact that this time is very low at 0.0023 seconds, on the right here we can see that it's actually 0.0037, or close to double. Additionally, the time taken to split the shares has also increased, however not close to as dramatically as what we see in the time to reconstruct and also the latency. So on this slide we can see the latency of all the combinations of variables visualized. It can be seen that the variable that contributes the most to the latency is the number of shares. For example, we can see steps between where s is equal to 5. So for example, here s is equal to 5. Both the variables are quite similar. The same goes for s equal to 4. There's a bit more of a change as t changes, and then back down to at s equals to 3. We can see that between all these there is a bit of a step. When we go up to s6 as well, there's an even larger step. And so we can see that if Sample Cloud wants to optimize latency, then the variable s should be kept low as possible. Now that we have the results of our preliminary investigation, we can start to infer some knowledge from the data we've collected and start making recommendations to Sample Cloud as to which combination of s and t they should use. We would recommend that they use s equals to 3 and t equals to 3 of the combinations that we tested, and this is because when we ran the program it provided us with the lowest latency or the best quality service. This is because the number of files being uploaded to the cloud and retrieved is the lowest here. When comparing the results of S4 and T3 and S5 and T3, it can be seen that the latency goes up dramatically as there are more files to be uploaded to the cloud. We would then also be able to make the conclusion that if they wanted a t value higher than 3, for example 4 or 5, or any number in fact, that using a system where s is equal to t would provide them with the lowest latency. However, they may not always want to require all of the created shares to reconstruct the secret, and subsequently we can also say that where t is equal to 3, or in fact any number, the lower s is, the lower the latency will be. Now, closing up, we have our group members and their contributions. For this project, the teammates were Elijah, who did the data analysis and visualizations, myself, Leon, who worked on the code and managed the cloud storage bucket, and Luis, who did a lot of work on the code. And all three of us together worked in collaboration to produce and present this PowerPoint presentation. Ultimately, we would now like to thank you for watching our presentation, and we hope that it granted you some insight and/or was helpful. Thank you.